Okay. Now I was just explaining how many choice variables you have. So you have n choice variables. So actually you have non-negativity constraints. Okay. And you have, in the general setup of the problem, you have more than one inequality constraint. Okay. And variable j indexes these inequality constraints. Okay, so that's the general setup of the problem, and you may imagine many economic problems actually fit into this setup, right? So let me show you a couple of examples. So in a typical utility maximization problem, you have maximize utility obtained from C1, C2, C3, let's say, right? By choosing C1, C2, C3, subject to some budget constraint. So you can write the budget constraint in this way, right? P1, C1 plus P2, C2 plus P3, C3 must be less than or equal to your income. And C1 must be greater than 0 or equal to 0. C2 must be greater than or equal to 0. C3 must be greater than or equal to 0. Okay? You may imagine a Cobb-Douglas function, a logarithmic transformation of it. So let's say a logarithmic transformation. So you have ln C1 beta ln C2 plus 1 minus alpha minus beta ln C3. Okay? So that's one such problem. I can show you another problem from firm theory or production theory. So you may imagine a firm that uses capital and labor, okay, to minimize the costs, subject to non-negative capital stock, non-negative labor, and then you will have the production target, right? So you have production function, and your production must be larger than some given level of output. Okay. You may imagine another type of problem. I mean, for instance, if you want to minimize, let's say, a loss function, okay? Suppose that this is a central bank. So how do I do that? So a loss function could be defined in this way. For instance, the inflation rate minus the target, okay? So this is your loss. You can put a parameter here, okay? Then, of course, depending on the macro structure, you are going to use, maybe your policy variable is the interest rate, and then you have, of course, actually you can do this as well. If this is output gap, okay, so you may imagine choosing an interest rate, okay, to minimize your loss. Why it is a loss? Because if actual inflation rate is different than the target rate, okay, either below or above, your loss increase. If output gap is not equal to 0, so if you are not finding the output gap at the correct place, at its correct place, which is usually 0, so you want the real economic activity at the natural level, let's say, then you have this. Of course, this must be subject to a non-negativity constraint, right? I mean, typically, there is a 0 lower bound, right? And then you have some Phillips curve. Okay, that associates, let's say, output gap and inflation. Okay, and of course, you also have in some versions some dynamic, some IS curve, let's say. Okay, so this is just very informal, but you can do stuff like that. You can imagine a government problem. Okay, so imagine that government want to maximize social welfare. So you can define social welfare in this way, let's say. So you have one to, let's say, let me use a different index here. Let's say you have households, okay, from 1 to H. Each household, for each household, you have a particular weight attached to it, and then you have the utility of this household, and you can suppose that this utility depends on your policy variable, let's say a tax rate or a transfer rate, or a couple of variables that you can use for fiscal policy. Okay, and of course then you will have a non-negativity constraint, and depending on the structure of your economy, you will have some inequality constraints, okay, such as total budgets, right? You collect taxes and you do some transfer spending, or you can extend this utility function in this way. So instead of just dependence on tau, you can assume that it depends also on the public good, okay? So then if that's the total, so you may imagine that total public spending plus transfers, okay, should be less than your revenues. Okay, things like that. So any type of, I mean, most of the static economic problems can be expressed by using nonlinear programming. Okay. Now the question is, of course, how to solve it, right? And here is the idea. This is from Takayama directly, so you can visit the text as well. So first, we define what we call a Lagrange function. Okay, and the Lagrange function is defined very simply: your objective function. Okay, your objective function plus this animal. Now, this is, you have to be careful in understanding that this is an inner product. Okay, so it is like this. From J1 to M, so for each constraint, you will have a term. So this is 1. You have lambda J, G of J, X. Okay? So this is your Lagrange. And as is typical, we first will look at first order necessary conditions. Okay? And then after we find solution candidates, we're going to look at second order sufficient conditions. Okay, and after doing that, we're going to realize if the problem has a solution, we're going to find that solution. Okay. Now, something is important here. We are going to focus on maximization problems because you can always convert a minimization problem to a maximization problem, as we discussed. And we will be focusing on non-negative Lagrange multiplier. So lambda is called the Lagrange multipliers. Okay, so we're gonna focus on non-negative Lagrange multipliers. For this reason, we're gonna write g of x in this way. Okay, the reason is that we want to associate lambda with the shadow price of our resources. Okay, let me explain that because this is essential. So this was okay. Where's the consumer problem? Okay, you see it? You see the consumer problem, fellows? Do you see the consumer problem?
Yes.
Okay. Thank you. All right. So in this consumer problem, when you write the Lagrange, you have something like this, right? C lambda. So C here is basically C1, C2, C3, right? So you have UC plus lambda, careful, okay? Because I want to convert this into this form, right? I want to convert this into this form. If you do that, you should realize the partial derivative of Lagrange with respect to income is lambda, right? So that's the key. For this reason, since this is a shadow price, since this is the marginal value that is attached to the income increases, then we must require lambdas to be non-negative, all right? Because there is no negative price. Okay? So, now we start looking at the first order necessary conditions. Once again, let me write the problem in general form. Okay. And here are the first order necessary conditions. Okay. Now for all I, all choice variables, we require this. The partial derivative of Lagrange at an optimum with respect to xi must be less than or equal to 0, and xi star times this derivative must be equal to 0, and xi star must be greater than or equal to 0. Okay? So this must be true for all of your choice variables. Okay? This must be true for all of your choice variables. Then, for all constraints, you have this. First, the constraint, of course, must be satisfied. Then, Lagrange multiplier associated with this constraint times the constraint should be equal to 0, and lambda j star must be non-negative. All right? Now, if you can find x star and lambda star that satisfy these things, this basically satisfy first order necessary conditions, and the solution candidate. Okay? Does everybody see everything I wrote on the board?
Yes.
Great. So these are the first order conditions. End of the story. Okay? But what are the meanings of these things? right? Why is that different? Why not just take the first order derivative and equate it to 0, right? Well, it's because we have non-negativity constraints. Let me explain the logic. Imagine a very simple function. Okay? I will show you 3 cases. This is x, just a real number, and this is f of x. Okay? Now, suppose that your function is like that. Okay? So you have right away a maximum, right? This is 0, by the way. So here you have x star greater than 0. Okay? And in that particular point, f of x star is equal to 0. So x star is a stationary point of f, right? The derivative is 0 at that point. Okay? Now look at this case. X star is here at 0. But still, we have the derivative equal to 0. Okay? So x star is equal to 0, but f prime x star is still equal to 0. Okay? Now there is a third case. Okay? Now once again, x star is at 0, but the derivative is less than 0. Okay? The derivative at that point is less than 0. So our purpose, since we have this non-negativity constraint, since that part, okay, is not admittable, right? Our first order condition cannot be just like that. This is not enough. Okay? We have to understand, especially when the optimum is at 0 and the derivative is negative. Okay? Now, if you go back to this, you realize one thing. Suppose that xi star is positive. Okay? Suppose that xi star is positive. If xi star is positive, then what does this tell you? If xi star is strictly positive, this tells you that this is 0, right? Because this is positive, then this must be 0. If this is 0, then you come here and equate it to 0. So this is the first figure, right? This one. Right? Now, instead, if xi star is 0, okay, then you basically learn nothing about the derivative of the Lagrange, right? Because this equation basically drops. This condition drops. So what do you have if xi star is equal to 0? Either this is true. This is the third case. Okay? Or this is true. And this is the second case. Okay? That's the idea. So what we want to do is to write a set of conditions that cover all these cases. And those set of conditions are these. Okay. Now, what about this part? The constraints. What do I learn from here? Well, very simple. Suppose that a particular shadow price associated with a particular resource is strictly positive. Okay? Now, what does this equation tell you? If this is strictly positive, then this must be equal to 0, right? So if it is equal to 0, remember the consumer problem. W minus P1C1 minus P2C2 minus P3C3 is equal to 0. Let's say at the optimum. What does it mean? It means consumer spends all the income. Why? Well, it was valuable. Okay? Why it spends all of it? Because it was valuable. Its value for the utility was strictly positive. Since it is strictly positive, the rational consumer used all the resource. Okay? So I want to introduce that. Instead, let me go green. If it is 0, once again, that equation drops. I do learn nothing about the constraint. Then I have two cases again. This one and this one. Okay? So what happens when this is true? When g of x star is greater than 0. So what happens here? I will show you here. The consumer at the optimum point may not be spending all the income, right? Income is greater than the expenditure. So again, I want to write a set of constraints, a set of conditions that allows the decision maker to poorly spend the resources. Why would I be doing that? Because depending on some utility functions, depending on some technological structures, a decision maker may find it optimal. Or the objective function is so ill-behaved, we want to understand what happens when a resource is not that valuable. Okay? Now, in the static problems, we do not see this frequently. We usually see lambdas are strictly positive. Okay, but in dynamic problems, it matters a lot when, it matters a lot whether you find, you extract all the resources, or you use all the resources you have, or you leave some resources behind. Okay, it will be more important in these dynamic problems, but the logic is same. If a resource is valuable, I want to consume all of it. If a resource is not valuable, I may either consume all of it again, or not consume it all. Not consume all of it. Okay? So again, I have to write these conditions general enough so that as you see, these conditions possibly there is a simpler way of doing that. Okay, so these conditions are then general enough to cover for non-negativities and resource waste. Okay, the waste of resources. Okay, that's the thing. So, any questions? Any questions or comments about all this for now? If you think about it, it's very simple. It's the typical thing that you always do. Okay? Utility maximization, cost minimization, but we want to do it more generally, okay, in a more robust manner, to cover any possible objective function, to cover any number of decision variables, choice variables, to cover any number of inequality constraints. Okay? So if you have no questions, I will switch to my whiteboard again, and I will show you the second order conditions. Okay. Demek ki herkes mutlu. All right. Now, the second order conditions. Second order sufficient conditions. Now, for this, we're going to have two theorems. They're directly from your book. Let me check. Theorem 2.2 and theorem 2.4. Okay? This year, since it is recorded, I am much more careful in citing the resources. So these are from Takayama's text. Okay? Now, theorem 2.2. Very simple. If F and GJs are all concave, then X star lambda star is a solution. Okay? In your text, it is expressed in, in terms of conditions. So these are the conditions that he uses. Okay? So that's the first part. Second part, additionally, if there exists X bar, so this means there exists, okay? This means there exists, okay? If you see that, the flipped E, it means there exists. There exists X bar in X, such that G of J X bar is strictly greater than 0, then M implies fork. Okay? Now M is again as being a solution of the problem. Okay? If you look at the text, M means X star lambda star is a solution. Okay? So you can, if this is called Slater condition. It tells you that, let me just check. Yes, this is called Slater condition and must be true for all J. Okay? So if there is a point, X bar within the domain, okay, that satisfies that. This is basically resource based, right? So there are some levels of your choice variable where you waste all your resources, where you can waste all your resources. Okay? If that's the case, knowing the solution tells you that that solution should satisfy first of the conditions. Usually we are not going to use that second part. Okay? But it is there. Most importantly, if we have concavity for both F and G's, then we are good. Okay, so if you look at a problem If you look at a problem, suppose that I've given you a problem that you will solve with nonlinear programming techniques. First, you're going to define the Lagrange. Then you're going to take the derivatives to write the first of the conditions. And then you're going to find x star lambda star that satisfy, okay, that satisfy those first of necessary conditions. Then this theorem tells you if your f function and your g functions, all of them, are concave, then the x star lambda star that you found is solution. Okay? That's the idea. Now let me show you theorem 2.4. Okay, so again, this is from Takayama, theorem 2.4. And here it goes. Let me check the notation. Okay. Now, there's something called quasi-concavity, okay? Before this theorem, I have to explain what quasi-concavity is, okay? First of all, it is less stringent than concavity, okay? So a function, if a function is concave, it is necessarily quasi-concave, okay? But if a function is quasi-concave, it may not be concave, okay? You see it? So it is less stringent. So even if, as in theorem 2.2, even if your functions are not concave, we will have a version of a second order sufficient condition that uses quasi-concavity. Okay? That's the thing. Now, let me explain what quasi-concavity is. So, I will show you. First, let's delete that. So, okay. So, now, remember the standard consumer problem with two groups. Okay? In that framework, you have indifference curves, right? Each indifference curve gives you a particular level of utility, right? If preferences are well behaved, you know, convex preferences, etc., you have this. So in that direction, utility increases, right? And there is this particular notion that indifference curves should not intersect, right? This is because of, you know, the structure of preferences, basically. Now, for quasi-concave functions, we will have something like this. So there will be a region, okay? So this will be not just a curve, but a region. So you can have an infinite number of points in that region, okay? In any direction. Now, any point on this region gives you the same utility, okay? So we will have some flat regions, okay? Some flat regions. Now, if you imagine the third dimension here, there is this third dimension, right? Utility. It is like a mountain, right? It's like an edge of a mountain. Let me draw it.